grab all four of those, okay, tests. All right, so what I'm doing today is I'm doing kind of a comparative review. I'm going to review the entire course. I'm going to show you if you do enough exams that these questions keep popping up over and over again. If you guys can see patterns, then you're well on your way to dominating this test, or at least getting the best grade possible. Okay? Yes, the best thing you can do, guys, grab one of each of those tests. Okay? And we're going to work on 9, 10, and 11. The June tests seem to be a new cycle. Okay, so if you ever work on tests on your own, you do a January or a August, they're actually kind of a revamping of that June preceding. So you should work on June tests. They're like a brand new test, and the ones that are more likely given. Some people say that January and August are a bit easier since they're a repeat of the June exam a little bit. Okay, only people who know that is the state. All right. So in any case, I'm going to be crazy and start in order. We'll go 1 through 5, the 3 tests. I'm going to I call this a sprint, okay, and I will have time for you guys to do all of these sprints, but I want to show you how these tests are similar. They're built in a similar way. It's not 100% valid, or they do change it up a little bit, but I would say that you're going to see something in this order the same way. Knowing where you are in the test is really important. So we'll be being crazy, starting in order with 2009. We're going to 9, 10, 11. We're going to do 1 through 5. Okay, so, and maybe I can turn the page. Okay. So we're going to start with 1 through 5. Now, in questions 1 through 30, you should recognize the fact that they go over the entire course 1 through 30. And then through 31 through 50, they start again. And these questions in 31 through 50 happen to be more two-step application, sometimes more math where you need a calculator. Okay? But, so 1 through 30 and then 31 through 50, they revamp. They go through the first unit to the last unit, depending on how your teacher taught it, but atomic structure is the first. So any case, which a subatomic particle is negatively charged? Hey, the entire course is based upon how electrons are shared, transferred. So when in doubt, you pick an electron. Now, let's just say that you just feel like you froze up. So many people don't recognize there's a table out there that tells you particles. People only use it for nuclear, but is your friend, okay, in this part of the test. So this is, go to the reference table, and if you don't have one, I'm going to go there. I'm going to go to table O. I call it table O because, I don't know, I kind of want to be from Brooklyn sometimes. So here comes table O. And you say, well, how is this going to help me, Mr. Grodsky? Well, it's going to help you because, and I feel like being blue today, whatever the color is. Right here, they call it a beta particle. I always tell my students, write an electron there. And what you should know from electrons or any of these type of nuclear or atomic type of equations, top number is mass, bottom number is charge. I know most of you said, I knew that the electron's negatively charged, but maybe they could have asked for a beta particle. Who knows? Now, you need to know this. They put a 0 here. That doesn't mean electrons are 0. Now, this could pop up. Electrons are 2,000 times lighter than a proton or a neutron. So, in reality, its mass is insignificant to the mass of the atom, so they put a 0 there. But I have seen questions where they want you to know that electrons are 2,000 times lighter than a proton and neutron. Hey, by the way, we haven't gotten there, but we will. We'll see this. Where is a neutron? Has a mass of 1, top number's mass. Proton, mass of 1. They have the same mass. Okay, the entire mass of the atom is due to the stuff in the nucleus. Okay, any case. Going back to the question. If I can do this fast enough, maybe we can. Christmas in July. I'll get a... okay, I'm getting it. So we went to 2009, back to that test. So clearly it's an electron. And I know you say, well, I knew that. That's an easy one. Okay, I get you. But I don't know if that's true for everybody. Okay, which element has the greatest density at STP? Let's go, quick. What do you know? Top of your head. Now, if you know this top of your head, you probably have no friends. That means you're doing what? Memorizing a place where there is information. This weekend I studied the densities of all the elements. Of course you don't know this. There's a place to go. And for this question, okay, I'll talk about two things, all right? Number one, where do you look for density? The most underutilized table besides table O, okay, is table S. Not enough people go there, okay? Not enough people go to table S. So let's go there. Let's be crazy and go there. Go to the reference table, table S. And why do I say it's the most utilized? Because some people like say, I don't know what I'm doing there. So in any case, go to table S, maybe. There we go, maybe. Now table S, now if you notice the choices they gave us, it was down the alkaline earth metals. I forget exactly, I think they had beryllium. All right, so we had density for beryllium, which is 1.85 right there. Then they had magnesium, all right, which was 1.74. And there is a trend here if you don't know it, and it's not a trend people talk about, because why would you have to learn it if it's right in the reference table? Okay, so what else? We have magnesium, beryllium, calcium is 1.54. Hey, what's going on as I go down the table? The densities are doing what? They're increasing. So who is on the bottom of that choice? I mean, if we can go to it, is radium listed there? Okay, so if radium is listed there, I'm going to go to radium, and we'll see. And then this is just table S question. Okay, so I should say, is density is listed there. I'm not going to spend any more time. Okay, all right. So going back to that question. All right. So here we go. Back to 2009. So that one is going to be radium. How do I know? It's the bottom. They get more dense as you go down. If you notice gold, platinum, they're toward the bottom. Okay, by the way, look at table S. It gives it information. People forget about it. 3. What is the mass number of a carbon atom that contains 6 protons, 8 neutrons, 6 electrons? Well, we just went over table O, or table O. What did table O tell me? Electrons are what? That beta particle. I make my students write a beta particle. There is an electron. We just saw that a neutron written in table O is what? And then a proton is written like this. So we took about protons, neutrons, and electrons. Beta particle, electron. Okay, where's the mass? The mass, of course, is due to the what? Protons and neutrons. Table O, as I like to call it, table O tells you that. All right? So please don't get these wrong. So in any case, first and foremost, all right, I have 8 neutrons. Hey, there's 8 of these. 8 times 1, I'll give you a calculator. 8, right? And then I get what? 6 electrons. Mass is 0. Now, people want to put what? How many people get this wrong and throw an 8 there? Okay? Say, hey, I got myself what? 8 neutrons. But what else do I have? 6 protons. So what gives the mass of the atom? Protons and neutrons. So I've got 6 of them. That's what makes carbon. And I've got 8 of them. 8 plus 6, 14. And you should recognize carbon 14 as what? Another concept. Another type of isotope of carbon. And how does carbon 12 differ from carbon 14? 2 more neutrons. They're going to ask that. There's going to be a part 2 question where they're going to say to you, hey, hey, whatever your name is. Okay, they won't say your name. They'll say, hey. Maybe they won't say hey, but they'll say, how do these differ? This guy's got more what? Neutrons. Hey, let's go to another part of the course. Okay? And I'm showing you how this is interconnected. What's the problem with carbon 14? Anyone know? It's radioactive. How do I know? And I know, Mr. Grodsky, we're not even there. But I'm going to show you the connections here. Why is it radioactive? Where is it? Isn't there a table? I call this table N. Na 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 na. Hey, hey, hey. The last table you should have learned. Selective radioisotopes. And look what there is there. Carbon 14. Why is it radioactive? Why do we use it for living? Carbon, living, organic. Oh my gosh, another connection. Why do we use this for carbon dating? To see how old something is. What's the problem that carbon 14 has that carbon 12 doesn't have? Well, this is really 6 here. If you're cool, you don't have to write 6. If you're cool, you know carbon means 6, right? I'm not sure. I'm not really cool, so sometimes I write like this. only carbon can become 6, right? 12 minus 6 is what? 6 neutrons. 14 minus 6 is what? 8 neutrons. And that works because of this in table O. Now, what's wrong with it? 6 neutrons with what? 6 protons. That's a stable nucleus. Ooh, stable nucleus. What does that mean? It's a nucleus that's going to stay there. It has low energy. You've got a big boulder in your yard, right? Let's say you don't. Let's pretend you got a big boulder in your yard. You know the things they bring them in sometimes if you can't dig them up when they build a house, but they have a big boulder. Is it going to blow in the wind? No. It's going to stay there because if something is stable, you need a lot of energy to move it, right? Stable means it's going to stay that way. This is stable, the protons. What's wrong with this? This is not stable. It's got a nucleus that's high energy. Who's been to the city, gone to the train station, and saw that unstable individual trying to sell them their new rap album? Happened to me the last time, okay? They followed us 17 blocks to Rockefeller Center, okay? Because I gave them eye contact. The guy's unstable. High energy. If you got high energy, what are you going to do with it? Give it off. Things that have high energy, give it off, okay? So this has a problem. And what the problem is, the proton, they're not cool, to what? Neutron ratio is not correct. How does it fix itself? How does something radioactive that has a problem in its nucleus, how does it fix itself? It gives off what? Particles. That's a major concept. So you may say, Mr. Grotsky, how did we get to nuclear chemistry? I want to show you how this is interconnected. And that way, hey, we can do this. Now let's go back to 2009 again. Christmas in July. 2009. And so the answer, of course, with 6 electrons, okay, 6 protons, I'm sorry, 8, it's 14. And so many students, party people, and people that haven't gone to the party yet, or they told you the address, you don't know where to go, okay, this is the answer here. Now, just for fun, I'm going to mosey on to number 30. Okay? Now, for those that just came in, you must understand what you're doing in this test. 1 through 30 goes through the entire test, the entire curriculum, from atomic structure to nuclear. 31 restarts it and does it again, but uses harder questions. Can you see number 30 here? A beta particle may be spontaneously emitted from a what? And I bet if I didn't have that discussion, you'd have a difficult time. If I was to tell you what nuclear chemistry was about, it's about the nucleus, not the electrons, not chemical reactions, having a problem. And that problem is that they fix it by changing their nucleus. It's not about electrons. Cross it off. Cross it off. If you're in a nuclear area, don't let them confuse you about chemistry. Chemistry is about electrons being shared, transferred, being able to move. All of chemistry is about the electron. Nuclear chemistry is about what? The nucleus where electrons don't exist. It's not even chemistry. It's called nuclear physics. I don't even know why it's part of this course. So they're going to do what? Always try to confuse you with chemistry questions. Cross out the electron. Cross out the electron. And now we're about who cares if it's a beta particle? Who cares if it's a alpha particle? Who cares what positron? They all emit particles to get what? To get stable, so they start from a what? And that's why your answer is 4. Okay? Look at 29. Which particle has the greatest mass? Where could I find that information? Table? No, you gotta say it right. You gotta say it right. Table. Oh! Okay? So now, I already know what that particle is. You probably do too, but people say, I don't know, I didn't study this. Okay? It's the same freaking table. Now, where's the mass number? Right there. And you guys should learn that alpha particles have the greatest mass. Why? There's a 4 over 2. What is it? What was it telling you? It's made up of, what's the bottom number? 2 protons and 4 minus 2? 2 neutrons. Hey, that's a slow-moving heavy particle. Of course, that's your answer. And that's why alpha particles are least penetrating. What does that mean? Alpha particles bounce off our skin. They're not dangerous to us. We have them in our homes, in our smoke detectors. Okay? Beta particles, they have almost no mass and a -1 charge. They go a little deeper. And if we had what? Gamma rays, no mass and no charge, they're the most dangerous. Okay? Okay, moving forward. Hey, just for fun, okay, and it is fun, because when you start seeing this, let's go on to 2010, go on to 30. See what kind of magic they show us there. 2010. And go on to 30. Am I going to find a nuclear equation there? A nuclear question? Oh my gosh. Okay? Which reaction is accompanied by the release of the greatest amount of energy? If you remember anything at all from me today, especially with nuclear, besides the fact we're going from an unstable nucleus to a stable, when they drop the atomic bomb, hey, 3 tests right there, 4 tests, okay? And grab the gift certificate for the free ice. Oh, they're gone now. Okay. All right. Okay. They're gone. I'm sorry. I only had one, and I took it. All right. Now the point is, what are they trying to do here in a nuclear area? Mix in chemistry with what? Nuclear, right? Now, not only that. Think about it. They dropped the atomic bomb in Hiroshima, and that's a pretty sad event. They're still feeling the effects because the radiation given off in the atomic bombs dropped in Hiroshima and Nagasaki are still felt today in 5th generation kids who are being born with genetic problems because of the mutations that arose from the radiation given off from that bomb. But that single bomb dropped in Hiroshima had more energy than all of the conventional chemistry bombs dropped in the entire World War II. Think about that. You must understand that nuclear, okay, energy is always greater what? Mass. I'm sorry, there's always a greater amount of energy in nuclear reactions or nuclear processes than chemistry, electron-based. And why? The reasoning is very simple. We're dealing with nuclei. Where do protons exist? In a tiny spot called the nucleus, right? And didn't Ernest Rutherford, Ernest Rutherford, okay, I don't know if people understand what that means, they were not in my class, but Ernest Rutherford found that the entire mass of the atom is mostly empty space, except for a very, very, very tiny center. That center is where all of the mass, okay, results. Remember, the entire mass of the atom is what? Due to the neutrons and protons that are in the nucleus, right? Now, electrons do have some mass. It's so tiny, it's 2,000 times lighter, but essentially, it's the protons and neutrons. Protons are what charge? If you go to table O, +1. And they're next to each other in that small area. What do positives and positive like charge do? Repel. So what's keeping them together? Something called the strongest force in nature called, anyone? The strong force, okay, why not? Now you don't have to know that for the Regents, but you have to know it. Anytime you mess with the strongest force in nature, you're going to give off the strongest energy changes in nature, okay? Very important. All right, so of course, cross-out combustion, that's a what? Chemical reaction. Cross-off electrolysis, that's where you add a battery in a chemical reaction. Cross-off oxidation, hey, that's where you what? Lose electrons, all of which are chemistry. Where is the only nuclear type of process? Fission, which is, you know, splitting of the atom. 29, listen, that's what? Decay mode, table N. Right off the reference table, I'm not going to go over it, okay? Okay, for fun, let's go to 2011. We did 2009, 10, 11, it's 11. Grab those 4 tests there. That student right here, she's in, what's your name? Paige. Grab a bunch of those pages, not her though. All right. Hey, I'm here all day. All right, 2000 and what did I just say? 11. My short-term memory's going at this height. Okay. This is fun for me because I can use this like new jokes. People don't know me yet. Okay. Sorry, people are like, who cares? It's not about you. Oh yeah, today it is. Okay, so 2011, I can do this. 18. Right there. All right, let's mosey on down to what? Number 30. How did I get to nuclear? All right, here we go. 30. Atoms of 131 spontaneously decay. Now, what does that mean, spontaneous? You're going to hear that word pop up in different parts of this course. Let me give you the visual. Does your room or box, wherever you live, garage, hey, I don't know. Okay? Does your area that you live, don't want to exclude anyone, okay, get spontaneously dirty or spontaneously clean? You ever walk into your room and say, whoa, it's clean now? I wish, look at this room. Okay? Or does it spontaneously get dirty? Did you try to make it dirty? No. So nature works in its ways. It works toward spontaneously disrupting things so there's more disorder. Things in nature work toward disorder. So spontaneous is a pathway that tells us without applying any energy, it happens. Okay, is a battery spontaneous? Is a voltaic cell, which is the same thing as a battery, spontaneous? Do we have a battery connected to a battery, connected to a battery? No, a battery by itself is giving us energy without us putting energy into it, correct? Just like our room gets naturally dirty. It's following the same laws. Hey, the best example is riding a pony. Okay? The pony takes me places. I don't have to add any energy. It's spontaneously taking me up the hill. But what if the pony doesn't want to ride anymore and I got to bring it back up the hill where we live? I got to carry the pony. Is that spontaneous? No. Because I'm adding energy. What's electrolysis? I use what? Energy, a battery, to make something that doesn't happen normally. Right? Hey, my phone runs out. Okay, I know they have the commercial now where you can crisscross some stranger. Okay, and recharge it. I'm not sure if I like that. I don't like my phone touching someone else's phone that, like, hey, can I get a charge? That just seems like, I don't know, that doesn't actually happen. All right. So the point is, I don't know where I got off the track here. We're going to get rid of what? Chemistry. All right, here we go. If I am decaying, what does that mean? It's changing into something else. What's the word here? It's spontaneously changing, but the changing, it rhymes with transmutation exactly. Transmutation, awesome. You guys are rappers, okay? I don't know, maybe not. So, by itself, iodine 130 decays. Hey, that's just like what? That's just like carbon 14 that we just talked about. Check it out. So carbon 14, okay, is right here. It's unstable. What does that mean? Its nucleus has a what? Problem. It wants to fix itself. So by itself, it's by itself. The room gets dirty by itself. By itself, it emits an electron out of its nucleus. We call it a beta particle. Got that from table O. And I can look that up in table N. If you go to table N, you'll see the decay mode of carbon 14 is a beta particle. Now, what does it decay into? This could be in your part 2 tomorrow. All the numbers on one side equal all the numbers on the other. What number plus a negative 1 is 6? Hey, slow down. I've got a fast calculator. What number plus 0 is 14? Oh, jeez. All right. Here's the biggest mistake people do. They say, okay, it's 7. It's carbon. Oh! No! Every element has its own. So this is what element? Atomic number 7, nitrogen. This is what they're after. I can do the same thing. Iodine 131. What's the atomic number of iodine? Over there, big numbers. 50, 53. By the way, table M, tell me iodine 131, what's the decay mode? What's the decay mode? What kind of particle? What kind of particle does it emit to get stable? Beta! Oh my gosh! And I don't know what beta, I go to table O and look it up for the symbol, and it's what? What does it become? What number plus negative 1 is 53?
54.
Say it like you're from Northrop at 54. Okay, good. What number plus 0 is 131? 131. What number, atomic number is 54? What's that? Xenon. Is this natural, spontaneous decay?
Yes.
Because by itself, it's doing it, just like your room getting dirty. This, my friends, is called natural transmutation. Why is it natural? By itself, when it was made, it had a problem. And now it's fixing its problem. Let's check this problem out. And this is something you have to know. Well, what is the problem with carbon 14? We talked about it when we first started. It's unstable in its nucleus. It's high energy. It does something to get stable. It has too many what? Neutrons. So this had what? 14 minus 6, 8 neutrons. How many protons? Cool beans. Now over here, how many protons? 14 minus 7. How many neutrons? 7. Anyone see what's going on here? Do you see the neutron to proton ratio is about equal? Hey, exactly. That's why it got stable. It changed its nucleus to get stable. And you've got to know one of the ways is the proton to what? Neutron ratio. By the way, carbon-12 is stable. It's not listed in table N as having a problem in its nucleus. Anyone tell me why? Neutron ratio is equal or appropriate. Hey, you learned something. Okay? And I'm telling you right now, they're going to ask you, is this artificial or natural transmutation? And you're going to say what? Natural. If it was artificial, that means we have to make it happen. For instance, I want to take a walk into nature. There's plenty of parks. See a babbling brook. Pick some natural flowers. Maybe eat some berries that aren't this color. Okay? All of a sudden, I see a particle accelerator tree. Or I pick a particle accelerator off the tree. What's a particle accelerator? A piece of equipment that's usually billions of dollars that men have to do, or women, sorry, man. Why do we say man? Okay? Humans made, all right, to slam these together. Artificial means I'm going to have another nucleus here that have to be slammed together. And why? What's in a nucleus? Tiny spot where all the positives are. When you slam them together, positives and positives are going to repel. So you need a piece of equipment like the relativistic heavy ion collider in Brookhaven National Lab to slam these things together. You need a piece of equipment. Anytime you see two things, it's being forced to happen. Is fusion and fission natural or artificial? Artificial, slow-moving neutron splits an atom in fission, or fusion, two light nuclei. My gosh, how did we get here? It's all interconnected. Okay, so let's go back to reality. Up there goes gravity, and let's go back to 2009. Sorry, but that's how it works. Okay. Okay, so where was I? 2009. 2000, I can do this. Okay. Go back to our sprint. Which element's a metalloid? Do I have to do this? Sure, why not? Okay, let's go quickly through the periodic table. Yeah, it's 3. Okay, but here we go. And I see, when I see a table, party people, I do this. Let's. I erase this stuff.
I got the answer.
You have the answer. What's the answer?
AS.
AS, arsenic. Don't be an arsenic and don't get this wrong. Okay.
Okay.
Okay. Now, when I see periodic table, party people, I do this to it. Okay. And I know I have issues, but again, let's do it big. Whoop. Stay here, and I don't know. I do. On my what? Staircase. And these two are the things that have 2 things. And I'm going to tell you right now, this course is about 2 things, yin and yang. Here's my yin, here's my yang. What are these guys?
Yin.
Metals. What's so special about metals? What's so special about metals?
3.
Right. There is nothing on the periodic table that can only become positive besides metals. I will give you, okay, monopoly money. That's $10,000. Well, forget it. I'll give you $10,000. I should say not monopoly money. I'll give you any kind of money if you can find me a metal that becomes negative. You can't. Metals lose electrons. Why? No! You gotta understand. Metals. Okay, check it out. What is the nuclear charge of lithium? Everyone gets this wrong. What's the nuclear charge of lithium? What is the charge inside the nucleus of lithium? Plus, does a neutron have a charge?
No.
In table O, there's a 0 below it. It doesn't have a charge. Now, in the same energy level, what am I doing as I go across? We're adding protons and electrons. Mr. Gratzky, we're also adding an electron. Remember, I say atom, you say what? So, good. Atom.
Neutral.
Louder. Atom.
Neutral.
Atom.
Neutral.
Just not feeling the energy here, okay?
Sorry.
Listen, listen. These are all atoms. They could say to you, how many electrons? And you would say what? 3, because if it's +3 in the nucleus, it's what? -3 outside the nucleus, which means the whole atom is neutral. So when lithium becomes +1, like a good metal, how many electrons does it have now?
2.
2. It lost 1. And when this becomes +2, how'd that happen? It lost how many? 2. It keeps losing. The question is why? Well, as I add protons to the nucleus, as the nuclear charge, this could be a Regents question where they say, what is the nuclear charge of beryllium? And people will say, oh, atom, 0. Not the charge of the entire particle that we call an atom. What is the charge of the nucleus? +4. Okay. Now, as I keep moving across the periodic table, what's happening to the nuclear charge? It's increasing in the same energy level. And you need to know the energy level is the same distance to the nucleus. So, if I'm lithium, compared to fluorine, who's got a nuclear charge of +9, its nucleus is 3 times stronger for electrons than lithium is +3. Did I do the math right? Isn't 9 3 times that? Thank you. Okay, so lithium in the same energy level doesn't have the same attractions for its electrons. So it can't pull them in. So lithium,
Oh my god.
okay, has this electron. Yeah, it's coming. Oh my gosh, oh my gosh. I hit somebody. I lost my electron pretty easily. Why? I don't attract it. Why don't I attract it? My nuclear charge isn't big enough to pull it in. Does it make sense that lithium loses? Yes. Now let's do fluorine.
Oh god.
Okay. By the way, this is a sash. Okay, a sash. I'm not choking her. This is like, okay, like a beauty contest thing. Okay. Now, if I'm fluorine, okay, does it make sense fluorine's smaller? Because fluorine has such a high number of electrons, it attracts the electrons, so its radius is what? Much smaller. Look up there, party people and people that want to go to a party. Look up here. What's happening to the size of the radius?
Smaller.
Because I'm adding more what?
Larger.
But Mr. Gronsky, I'm adding more what? Electrons. Who's lighter? Smart car, let's pretend has the same attractive force, -1, as a tractor trailer, who's +1. Who's going to move? They pull on each other. Let's pretend the smart car and the tractor trailer have the same torque. Who's going to move?
Smart car.
Right, because it's
Lighter.
exactly. Electrons move in. And that explains everything. What's the word for attraction for electrons? You better know it. Electronegativity, listed in table S. And what's happening as the atom gets smaller? Its attraction for electrons increases, correct? Yeah? That's true. Now, what happens as you go down? Don't I add in the shell of electrons? So they're physically farther away? Okay. So what I'm getting after here, and I know that I'm off the reservation here in terms of what I'm talking about, metals lose because they're so big. They become positive. We have a word for that. Oxidation, Leo. Who gains? Ger. These guys are smaller. Hey, think about it. I'm a metal. I'm going to hold on to that electron so loosely, but a non-metal does what? It attracts its own electrons and fantasizes about gaining more. And it does, eventually, to get stable. And who has properties of both? What defines a metal? What defines a metal? They are big radii, which means they do what? They attract electrons weakly, loosely, or strongly. Weakly, that's why they lose them. The reactivity of metals, oh, table J, sorry to go there, is based on how well they lose electrons, right? And if I have two metals in a voltaic cell, how do I know which one's the anode? Anox, oxidation, losing. Who is better at doing this?
Metals.
Is the anode. Correct? Cool. Gur, gaining electrons. Why do they become negative? They're the only elements that can become negative. Okay, I can't make my point any clearer. Metals can't because they have high attraction, called electronegativity. Now, there's another word people forget, ionization energy. If I'm a big old metal holding on to my electrons loosely, not much attraction there. Okay, is it going to take much energy for John to pull this away? John, pull my electron away.
Ah, Jesus, John, you ripped it.
I didn't know he was going to hold it.
Whoa, okay. Okay, easy, John. John, jeez. Listen, it's just a doll, John. Okay, all right, now.
Idiots.
Stuffing's coming out of it. All right, now. Listen. Did it take a lot of energy, John?
No.
No, because I'm holding on weakly. So what do you know about the ionization energy of metals? Are they going to be high or low? Low. And as my metal gets bigger, because I have what? Shells of electrons. They'll ask you this, party people. As this gets bigger, is it easier to move or harder to move if electrons are physically farther and farther away from the nucleus? Easier. You can look at table S, but they'll ask you that. Now, let's do a non-metal. I'm fluorine. I'm holding on tightly to my electrons. I have high electronegativity. Now for John to pull this away, come on. Oh, jeez! Okay, he knew that was coming. Thanks, John. All right, now, that took a lot more energy. Why? Because I'm holding on. Let me see, Mr. Grodsky, I see that. Why are you pounding that? Because they're going to ask you that. Okay, and of course, what defines the nonmetal? Small radii. I attract electrons. That's why I'm small. I hold on tightly. I gur. I gain them because I attract. What defines these? Loosely held electrons. I lose them, I become positive. Hey, let's figure this out. If I become positive, do I get smaller or bigger? If I lose an electron, do I get bigger or smaller? I lose an electron. All these metals, what do they do? How is their ionic radius different from their atomic radius? How is atom, neutral, when these are neutral, how do they differ from their ionic radius? So when they go from 0 titanium to +3, do they get bigger or smaller? Is their ionic radius, the radius when it's a charged atom, they get smaller? Why? Right, if you forget that, lose weight, you do what? Get smaller. Okay, now the real reason is if you lose electrons, like metals do, because they hold onto them loosely, the protons outnumber electrons, you pull them in. You don't have to do that. But for the regents, hey, they lose electrons. Now, these guys gain electrons. Hey, you gain weight. Your ionic radius, which would be negative, you get what? Bigger, because you gain weight. Good? All right. What else defines nonmetals and metals? Okay? Because their electrons are loosely held, electrons conduct electricity. What two ways do you have to know for the regions how electricity is conducted? You have to have free-moving charges. Either you have free-moving ions called electrolytes in solution, or free-moving electrons. Doesn't a metal conduct electricity? Doesn't copper wire conduct electricity in your home? Yeah, because when copper bonds with itself, called metallic bonding, they have all these loosely held electrons. Here's an electron, here's an electron. Hey, I'm repelled by this negative charge, so what do? I move, and I repel this one. And all of a sudden, I can see how this conducts a charge. If I'm a non-metal, okay, John, come up here. Soft clap, okay. That was almost a mocking clap. Non-metals and non-metals are involved with covalent bonding, aren't they? We're fighting. I have high attraction, you have high attraction. These electrons aren't free to what? Move. So if something's negative here, it doesn't move. That's why what? Non-metals are terrible conductors. They're called what? Insulators. Wow, it's a mocking laugh. Sorry. Okay, let's go back to the question. I don't know what questions we're on, but we're going to see all of this happen. I'm getting excited. Okay.
I was there.
Was I? 2009. I know, I'm all over the place, but I'm tall, and I can do that. Okay. Say number 4. So, of course, arsenic is on the staircase. Number 5. Who can be decomposed by chemical means? What's a chemical bond? What's a chemical change? They love to ask about this, and people get this easy stuff wrong. Yeah, In order to be a chemical change, chemical reaction, you have to break bonds and reform new ones. Anytime you've got a chemical change, you're making something new, which means there's going to be brand new properties. All of a sudden, there's a new smell in my room. All of a sudden, there's a new odor. All of a sudden, there might be a change of energy, which could be chemical or physical. But when there are new properties being developed, that means new bonds are formed. Okay? So the question is, who has bonds? Aluminum is an atom. Okay? Octane, you should know from organic chemistry, is carbons and hydrogens in a single bond. That's got bonds. Silicon, element. Xenon, element. So these represent what? 3 atoms, okay, that are not don't have any bonds. So the only one with bonds is 2 classic questions. Sometimes you see this as a what? As a picture. Okay, number 6. An element that's malleable, good conductor of electricity, could have an atomic number of. Oh, wait a minute. If you're a good conductor of heat electricity, you must either have free-moving ions or free-moving electrons. Since we're talking about atoms that are listed on the periodic table, we're not talking about ions. What am I looking for here? A metal. And an atomic number of what? Okay, 16 and 18 are third row elements that are toward the right. So where's my metal atomic number? 29. And where's my metal? Below my staircase. By the way, what's malleability? It's the same thing as ductility. Malleability means that I can heat this object and I can hammer it almost into any shape. Why can I do that? Because metals bond by a special way called metallic bonding. It's the way they don't talk about. Someone just said it's a sea of mobile electrons. Now, how does a covalent bond work? Me and John showed you. I donate one, he donates one. We're both fighting for it, and that's a covalent bond. Metallic bond is kind of like that lazy neighbor who doesn't cut the grass, doesn't care. His kids are all over the neighborhood, but he knows other people are taking care of his kids, and maybe the kids from the other part of the neighborhood are in his grassy knoll because he doesn't cut it. The point I'm trying to make is metallic bonding is kind of chill. I'm going to bond with John over here, and I'm going to bond with the rest of you guys, and I'm going to be the nuclei of atoms, and we know that nucleus of metals attract electrons strongly or weakly. So weakly, if I draw this picture, and sometimes you see this picture, if I draw this picture, you see the nucleus of metals in this metallic bonding, where the electrons are free to move throughout the entire crystal lattice. They're attracted enough to stay within that crystal, but not attracted so strongly that they stay with each atom. They call it a sea of mobile. So every nucleus of a metallic structure is what? Attracted to every other person's electrons in all directions. Think about it. My bonding in a metallic structure is that I'm attracted to everyone's electrons simultaneously. So you can bend me, twist me, and shape me, I'm still attracted. Covalent bonds? You give me a stress right here, it's going to break. Who saw the racquetball dropped in liquid nitrogen this year? Maybe not. Why does glass break? Why does china break? Clay pots break. Anything non-metals are brittle. Okay? Because of that. You're putting stress on only where the bond is. Okay? So, here we go. Number 7, mole concept. A mole of sample of krypton gas is a mass of what? Okay. I don't want to get into it, but krypton, they decided what a mole was. They decided we needed to count particles to figure out chemistry. Bottom line is the atomic mass of an element became what the mole was. Okay? Keep it that. So what's the atomic mass of krypton? Okay? Is it 84? I think it's 84. Okay, just look that one up. Okay, number 8. Okay, atom in the ground state. Whoa, what does that mean? Atoms in the ground state. Put it this way. If you're in the ground state, here comes that word again. Are you stable or unstable? What does stable mean? Low energy. Right. That means you're going to stay there unless someone adds tremendous energy to change you. You've got to get these words down. They don't just mean one little thing. They are basically used throughout the entire course. So if I'm a stable ground state, okay, they don't have to say this. They're just telling you it's stable in the ground state. But of course it is. Okay? Now, this atom could be what? Now they're telling you that it has the lowest energy in the ground state. Who has the least ability to do anything? They're screaming to you which family of elements? The noble gases. Noble gases don't bond. Why? Because they have what they call a very stable electron configuration. And everything is filled. Okay, so when you fill a shell, that means you have low energy. Okay, so they're asking you which one's a noble gas. No problems with that, right? Okay, we're good with that? Sodium explodes in your mouth. Why? It has one electron away to be lost to get stable. Chlorine gas will kill us. It's what? One electron to gain on metal to be stable. It's going to react. Okay? Aluminum. Okay, it's a metal. It's going to lose 3. Okay? So stable, low energy. Number 9. An atom, you don't have this 4 tests to pick up by page. A bunch of pages next to page. Sorry, I'm using that twice. But Donna didn't hear that joke yet, so I went there. Okay, here we go. I love this question. We kind of hit on this already. Oh my gosh, Oshkosh. An atom of an element has a total of 12 electrons. Ding, ding, ding. Whoa. I hear atom, you say what? Therefore, the protons must equal the what? Right. So don't you know what element this is already? Atomic number 12. If you go to your reference table, is magnesium. You already know what the atom is, right? They say atom, I know it's neutral. I know that the protons always equal electrons. So I know what atom this is. So, okay, fine. An ion of the same elements a total of 10 electrons. Which statement describes the charge and radius? Now, if you're lost, okay, I'm going to go there because I can. Here's my table. And we're talking about, maybe, magnesium. They're telling you the charge this atom loves to become. Of course, it's going to lose 2 valence. By the way, why does it lose 2 valence? What is here? It becomes stable, lower energy when it has what? When the remaining electron configuration is filled like a noble gas. That's the driving force. You should know that. Because they could ask you this question. Magnesium plus 2 has the same electron configuration as who? And you would say what? Who's 2-8? 2-8, and that'd be neon. Okay? But back to the question. Magnesium's a metal. What does it do? It tells you it loses 2. And what did I teach you? Metals, when they lose, get bigger or smaller? Smaller, but the wording gets people. We have the atomic radius. We know it's starting out big because it has what? A low number of protons in its row, nuclear charge, right? And when you lose weight, you get what?
Big.
Lose weight, you get big?
Oh, Jesus Christ.
Yeah.
Oh.
I'm going to go on a diet to get big. No. And why do you get so religious all the time? Okay?
I'm very religious.
Okay. I see that you're not. Okay? Say Buddha or something, all right? Oh, my Buddha? Okay. All right, thank you. Or if you want to do something non-religious, say, oh, Confucius. All right. Now, here we go. The atomic radius. If this is going to get smaller by losing electrons, hardy people, I can't say this enough. Whatever's in the multiple choice that I'm covering is the same stuff in the part 2. I'm going to show you that if I have enough time today. This is a question they'll ask you in part 2. Explain why magnesium gets smaller. And all I have to say is it loses electrons. Okay? So what? Its atomic radius as an atom is bigger than its what? Its ionic radius. Don't get lost in the words. And that's what people get lost with this question. As an ion, it got smaller. Its ionic radius got smaller. Okay? So here we go. So 2009. Here we go. So, the ion is positively charged. I know it is because it's a metal. Hello? Plus 2. Okay? So I get rid of these 2. And its radius is smaller than the radius of its atom. Right, so number 1 makes sense. Okay? People get this wrong all the time. They get messed up. All right. Okay. Careful, careful, careful. Can't say this enough. When they talk about, and they will, talk about polar versus nonpolar, you need to tell yourself, am I talking about the bond or the molecule? People don't realize there's a difference. Okay? Now, let's stop for a second. They're not asking for this, but they could. What is a non-polar bond? First of all, what's a polar bond? Yes, sir. Okay, good. I like that. Okay, now think with me for a second. Can something ionic which becomes, now by the way, what's an ionic bond? This is very important.
A bond between a metal and a
Okay, it's actually more than that, but that works. If I write NaCl, you're right, a metal and non-metal. And the reason why that works, metals become what? Positive, non-metals become what?
Negative.
Right, notice I have the bigger negative. Now when I write NaCl, does that exist in nature?
Yes. Sodium chloride.
It's such a lie, it's like a Kardashian wedding. They're not really together. Okay? If I write NaCl, here's how it looks, party people. Here's how it really is. Here's Na plus, attracting what? Cl negative, Cl negative, Na plus, and it keeps going. Where is it?
Wait, this thing?
Yeah, thank you.
This thing.
This is Jeopardy. No, sorry. This is ionic compound. They make crystal structures. If I'm positive one in all direction, will I only just attract just one Cl? No, it makes a crystal structure. That's important. And how do we write this? The lowest ratio called what kind of formula? Empirical. We write ionic compounds empirical. Hey, when you're writing formulas and you say, okay, what's the formula of calcium oxide? You know calcium goes in front. You look up calcium. It's an alkaline earth metal. It's +2. Because you heard "ide," you know it's binary. There's just two elements. There's oxygen, and you check out upper right-hand corner of the non-metal who gains electrons as -2. Oh, lost an ion. Not my marbles. Okay, let me go get it. Okay, notice which one's bigger. Who's bigger? The non-metal, because it gains. It's ionic radius. I know it's kind of far up there. Okay, how about up here? Sorry. Who's bigger?
That one.
Okay, this blue, this red one here, blue one, I guess, purple, blue. That's what ion? Sodium. It lost electrons. That's your chlorine. Now, that's what this is. But anyways, any case, back to this. What do you guys do to do this? You learn a crisscross method? Well, some people did. Okay. So a lot of people, maybe some people do this, but that wouldn't be good, right? Reduce to lowest ratios. Salts. Does calcium oxide exist like this? No. It exists in a crystal, the lowest ratio of the ions. Now, how did an ionic compound result? You have to know this, and I'll ask you this. A metal does what? Do I have to bring the doll back out? What does the metal do? Keep that visual. Did it lose the doll? It loses electrons, so it becomes positive, right?
Yeah.
And who does it lose it to?
A non-metal.
Oh my gosh, have you done anything where electrons were transferred? Have you ever done anything called redox?
Oh, yeah.
Oh my gosh! Didn't say God, or Allah, or Buddha. Okay, not getting religious here.
Idiots.
Oh my nothing. See, atheists too. All right, now point is, calcium oxide is a salt, is an ionic compound because there was a redox reaction, a transfer of electrons. Now, is that a polar bond? Can something that's sticking together by positive and negatives, although they lie to you and write it like that, is that a polar bond? Because you said polar bonds when you have the same electronegativity. These have different. Yeah. Sodium is about 0.9, and I'm a loser for knowing that. Okay? And then the chlorine's about 3.0. You check out table S.
That would make it non-polar.
Well, why? Well, don't learn your rules. The 1.7 is something they pop up. If the difference in electronegativity is greater than 1.7, you subtract them. We say they're ionic. It doesn't always work, but the point is, it's a good kind of leveling place to look. The bottom line is, the difference in electronegativity is so great. When you have nonmetals, gaining, Leo, there's going to be a redox reaction. There's going to be a transfer. This cannot be a polar bond. Can't be a nonpolar bond. It's ionic. Asking if something that's ionic, if it's polar, is like asking number 5 if it has marital status. Doesn't make any sense. Is sodium dating someone? No, of course not. It's ionic something. It's not even live. Don't ever fall for that. And why it's not polar? There's no electrons on either side of the bond. They're already transferred. So what's a polar bond? What's a polar bond? A polar bond is between two nonmetals. Yeah, well, not diatomic, but listen. Here's the thing. Here's a visual I want for you. Before I go to work every day, I give my third grader a rope, and we have a tug of war. I want you to have this visual. I want to feel like a man, so I want to win every day. So I leave the house a winner every day. Now one day I'm going to lose, but not yet. I don't let him win. So I give the rope to my third grader. We pull, and I pull as hard as I can. I pull the rope right out of his hands. He falls down. He's crying. I stand over him and say, "Who's your daddy?" No, I don't do that. I give him gloves. Okay? So the point is, I ripped the rope right out of my son's hand. Why? Because I'm pretending to be the what? Non-metal. My third grader wasn't as strong. There was a transfer that made charges, and charges stick together in a crystal. That's ionic. Now, when I have a tug of war with my evil twin Mongo, okay, who's a little bit stronger than me, we have a tug of war. He pulls the rope a little closer, but because our electronegativity is very similar, our strengths are similar, both adults, okay, he works out a little more, okay, we're forced to share the rope. That's covalencing. That's a covalent bond. So check this out. Hydrogen and chlorine. 1, 2, 3, 4, 5, 6, 7 valence, right? Hydrogen has 1. I'm going to draw the pair closer. I'm showing unequal what? Sharing. This is 3.0. This is 2.2. Why is the electron pair closer to chlorine? And they'll use unequal sharing. That's a polar bond. What does polar mean? If someday I come into classroom and I act like this, okay, boys and girls, we're going to learn about, and the next day I'm like this, wouldn't I have different personalities? Polar means differences. Isn't on a different side of the bond? This has what? More electrons. This side has less. Is there differences here? That's what a polar bond is, unequal sharing. And we make this side a partial negative. The reason why we use that partial sign, for those that were Miss Pafal's class, is because those electrons are not being transferred yet. Okay? It's not a complete negative one. And this is the positive end. Okay. What about nonpolar bonds? Hey, chlorine. Bonding with chlorine. Why is this right down the middle? They both have what? The same. They're going to ask for that. How about this one? What kind of bond is here? Remember, two different nonmetals must have two different electronegativities, right? So polar bonds are easy, two different nonmetals. So what kind of bond exists here? Polar and nonpolar. Scream it! Polar and nonpolar. Ionic. Neither. Metal, non-metal means transfer. Careful. Okay. Now what about molecule? Hey, check this out. We talk about the bond. I'm talking about how it's sharing what? Between the atoms. Can we see there's an asymmetrical distribution of charge between the atoms in a bond? That's why this is polar bond. Now, if I draw a molecule, stay with me, and more of the negatives are on this side. We call this the negative side, or the partial negative. If the entire molecule has an unequal distribution, not just the bond is polar. One way to know that, very simple, we'll just keep it simple. If it's symmetrical all the way around, like CH, look at this guy right here, methane. Are these polar bonds? And they will ask this. That's the reason why I'm going over it. I'm not just going over the problem, I'm going behind what's behind the concepts. They'll ask, is this a polar molecule with polar bonds? Which of the following is a nonpolar molecule with, they'll do all that. So which of the following, they could have said, which of the following is a nonpolar molecule with polar bonds? Carbon and hydrogen, do these have two different electronegativities? Are they both nonmetals? So they're covalencing, right? Actually, carbon is a little more electronegative. So the bonds between the elements are not symmetrical, correct? But if you look at the entire molecule, aren't they equal in all direction in their unequalness? That's right. And that's a nonpolar molecule because everywhere the polar bonds, although unequal sharing, are unequal sharing in all directions. So to answer who's a nonpolar molecule, find the one that is symmetrical. Why is HCl polar? It has one polar bond, so it's a negative side. There's No symmetry there. H2O. Don't draw H2O like this. That's looking down at it. Okay, you may confuse yourself. Those two lone pairs are going to bend it downward. And because it bends downward, hey, you've got some asymmetry. Let's put the electrons in. O is more electronegative than H. So where is the negative side? Where's the positive side? Asymmetrical distribution. Who's the same all the way around? Good enough. All right? Oh my gosh, look at this, number 11. Compound XCl is classified as ionic if it represents the element what? Well, if that is a nonmetal who becomes negative, is -1. I need something that's positive, not partial positive, but it's positive. Nonmetal, 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 metal. So in this case, metal and nonmetal work here. Okay, 3. But in number 11, they could ask you, why is that ionic? And you should say there's a what with electrons? Sharing or transfer? Transfer. Okay? Now, here's a great one here too. Classic Regents question. The chemical bonding in sodium phosphate is classified as what? Okay. Between the sodium. What do we got here? Is there real 3 sodiums? What is this? I see a metal in front. Isn't metal going to exist as Na+? What is this PO4? Anytime you see a group of nonmetals, I say go to the what the heck is that table. The what the heck that table, in my periodic, not that, my what the heck is table E. So table E, my friends. And my enemies if you hate this. Okay? And I get it, it's almost over. Table E is the what the heck is that table. It tells you what these groupings, oh my god, there's a bunch of elements bonding. No! PO4 is a phosphate. It's a what? It's a cluster of nonmetals that act as a single unit. PO4 is -3 as a single. Now, because it's -3, we need what? 3 of these. Sorry for drawing them different sizes. 3 of them to balance that up. So, does this exist like this? Is this how it exists in nature? That's a lie.
It's like a crash.
Exactly, it's a lie. What is it really? Na+, attracted to a what? PO4 -3, into what? Na+. Now the crystal instruction here is what? A little bit different. It's not a 1-to-1, it's a what? It's a 3-to-1 crystalline structure. Bottom line is, what's the empirical formula? There's an entire crystal, it's ionic, okay? It's going to exist as a crystal, and there's going to be 3 sodiums per 1 phosphate in the entire crystal. That's how you're going to see this. Don't fall in love with that. So now, I think the question was, what kind of bonding exists? Well, first of all, how does a sodium attract a phosphate? How do different ions attract? What's that bonding called? Ionic. Great. So that's ionic. And that occurred because these are charges that were due to transferring electrons. Good. Now, inside the phosphate ion, let's write it bigger. And by the way, you don't have to know this, but PO4 -3 looks like this. Can you guess what kind of bonds exist? We like to use brackets for things that are charged. Can anyone guess what kind of bonds exist between phosphorus, a nonmetal, and oxygen, a nonmetal? Covalent. So this is actually the structure. You don't have to do this. But these are covalent bonds. And why does this work? Because the whole structure gained 3 to make it work. That's what PO4 is. It's a cluster of nonmetals that collectively act as a single unit. So inside, between the nonmetals, you've got covalent bonds. Understanding why will keep this with you. Okay, so back to the question. All right, hopefully. 2009. Christmas in July, sorry. You may say, Mr. Gross, we're not moving fast. We're covering so many different concepts. Okay. What's that?
We're going on.
Yeah, thank you. Okay, 13. This is another classic question that people get wrong. Which element is composed of molecules that contain multiple covalent bonds? Okay, I see people get this wrong all the time. Now, chlorine is easy because chlorine, look at it. How many electrons does it need to share to be stable? One, so it makes one bond. Oxygen needs how many electrons to be stable? Oh, so it needs two bonds. Nitrogen needs how many electrons to be stable? It has three bonds. So which one of these needs more than one electron to become stable? Nitrogen. Now, if you don't like what I just did, let's do it here. Nitrogen has how many valence electrons? It is 2-5. How many electrons are on the outermost energy shell that's the most unstable? 5. So I draw 5 dots. 1, 2, 3, 4, 5. Because if you don't like what I just did, okay, you could do Lewis dot diagrams. Here comes another N. It also has 5. I start with one bond. And then I evaluate. For those that do not like to do Lewis dot diagrams, I evaluate with circles. You don't have to draw circles, but I do to evaluate. Does nitrogen, by sharing, they're forced to share because me and Mongo pulling, we both have similar strengths, right? In this case, this bond is a what? Ionic, polar, or non-polar bond? Non-polar covalent because they're sharing equally. They both have the same electronegativity, right? Okay, you see how this stuff is not just memorized per question, it's connected. Now, this guy feels like it has what? 1, 2, 3, 4, 5, 6. Both nitrogens feel like they have 6. What do they want to feel? They want to feel like they have 8. So what do? You add another bond. Now evaluate. 2, 4, 6, 7. Both of them feel like they have 7. No, the octet rule. So what do? Add another bond. And there you go. And what is a bond? Because here's what they're going to ask you with. They could say to you, in N2, how many electrons are shared? You've been down there. How many electrons are shared? And of course you would say 6. Then they could say to you, how many pairs of electrons are shared? 3. Careful. And they won't give you the structure. How about they do this? Check this out. What if they say, hey, I have F, just drawing it subtly, Fe. And they'll say to you, how many pairs of electrons are shared between the multiple bonds? Ene is how many bonds? 2. If you don't know, table Q is your friend, right? So how many pairs exist between the carbons? 2. They could ask you the total number of electrons, and that would be fo. Say with me, fo. Fo. It feels good, right? Yeah, you feel edgy when you say fo. Okay? Hey, there's the 3 tests right there. Next to page. Here's a bunch of pages there. Okay, it's less funnier, but you didn't hear it yet, so. Okay. I know. Okay, I'm going to stop here, and now we're going to quickly go through a chase, or I say a sprint with the other tests. And I bet all the extra stuff that I pulled out from those questions appear in other tests. Let's go to 2010. And that's what you want to do. You want to see patterns. Okay, so 2010, I can do this. All right, woo! Rotsky, it's crazy. It's tall. All right. The gold full experiment. Ernest. Okay. Composed mostly of empty space because alpha particles did what? Now, if you forgot this, couldn't you go to table O and find out that an alpha particle is really what? What was an alpha particle? It's really what? You go to table O. Table O, yes, the helium nucleus. Good. It's helium nucleus. The birth of helium is by alpha particles that are released and they gain 2 electrons as they come up. Pretty cool. So this is really what? How many protons? 2. 4 minus 2, how many neutrons? And that's the particle. What is the charge of a helium nucleus? What's the charge of any nucleus? It's positive. They call it a nuclear charge. They're going to ask you, they'd be like, it's an atom. No. So if something is positive, and I shoot it at atoms, not the guy atom. Okay, any atoms in here? Of course there's atoms in here. Sorry. I was waiting all day for that. Okay. Now, what do we know? The nucleus of an atom is a tiny, 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 tiny part of the total volume of an atom. Think of Yankee Stadium. Put a baseball at second base. The entire mass of Yankee Stadium is in that baseball. And that baseball at second base has all its mass and all of its positive charge. So when I shoot another baseball at Yankee Stadium, what are the chances of hitting that baseball? Very, very tiny. But once in a while, that baseball of +2 hits the nucleus of an atom, and just by chance, if it gets close enough, it's going to deflect away because the nucleus is positive. Ernest Rutherford discovered the nucleus with the gold foil experiment. But how does this tie into the stuff I taught you? The mass of the atom is based upon what instead of nucleus? Protons and neutrons, if you've been here earlier. Okay? So, because most of his positive charges passed through the foil, it was empty space. You probably didn't need all the extra stuff there. 2. Who's located in the nucleus of a carbon atom? Okay? Protons and neutrons, because that is the part of the atom that has what? Mass. And in table O, do we know? Table O, we have what? Neutrons are what? Hydrogen is here. The mass of the atom is those particles in table O. That's how they asked for it differently. Oh, I'm sorry. Which part of the helium atom is positively charged? There we go. There we go. The nucleus. Not the electron, which is what? A beta particle in table O. Isn't that this?
Oh.
Yes, table O. So who is positively charged? The nucleus. And they're going to ask for it differently. They could say to you what the nuclear charge of xenon is. The protons. Okay, get that down. People get confused. Okay, folk. The mass of a proton is equal to the mass of what? In table O. I can't make this clear enough. 1 for the N. Here's the proton. Table O. Okay, if you don't, go check it out. Neutron, proton, same. Same question. Here we go, number 5. Love this question. At STP, solid carbon can exist as diamond and graphite. Compared to the molecular structure, the chemical properties. I want you to know this, okay? Structure is king. Say it with me. Structure is king. Chant it like we are some kind of outpost in Wyoming, okay, that is in some kind of cult. Structure is king. Now, you're not saying like it's a cult yet. Structure is king. And now look crazy when you say it. Structure is king. Good. Now why do we say that? Because when you change the structure, you change its chemical and physical properties. And now the question's over with. We all know that diamonds and graphite are completely different. Nobody writes with it. This is graphite. The tip of your pencil is graphite if you didn't know. It's not lead, right? So it's carbon-based. No one writes with a diamond ring and wears a pencil. They clearly have different properties. So they have, if they have different properties, don't they have to have different structures? Correct. Here is the structure of Here is the structure of graphite. The carbon atoms actually slide off. Here is the structure of diamond. They're made of pure carbon. What's the difference? The structure. Hey, why does organic chemistry have isomers? What are isomers in organic chemistry? Mrs. Grosky, we're not doing organic chemistry. Yes, you are. Why do we care about isomers?
Oh God, that's isotopes.
Again, here we go. At least it brings. Okay, why do we care? Well, I learned that an isomer, memorizing, is what? Same what? I don't want you to forget this. Okay, so party people and people that are trying to go to the party, or people not interested in the party, or like some people out there, you tried to go to the party but they gave you the wrong answers. Okay, now, watch. Here is 1 propanol. Here is 2 propanol. This is important. Why? Here we go. Prop, how many carbons? Table P, propeller. 3. So 1, 2, 3. See the AN there? That's an alkane, table Q. Single bonds. Okay, the OL is the table R. That's an OH group. The OH group in table R is an R, the rest of the organic compound an OH. So on the first carbon, I have an OH. Fill in the rest so that every carbon has what? H's are 4 bonds. 2 propanol. 3. 1, 2, 3. Ane. That's to A. Single bonds. Okay, 2, I have the OH group here. Let's do the molecular formula. 3 carbons, C3, 1, 2, 3, 4, 5, 6, 7, 8. We appreciate organic chemistry. How many O's? Good. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. 1 O. They have exactly the same formula. But IUPAC has different what? Names for them. Why do you think they're giving them different names?
Because they act differently.
They act differently, correct. Because their structure is what? Change the structure, change the properties. And for you to always remember this, if I was to drink this, I would get drunk. Intoxicated with an upset stomach. This looks a lot like ethanol. There's one more carbon, so it doesn't act exactly like ethanol, but you would get intoxicated. It's an expensive alcohol, so you would never make it naturally, and besides, it doesn't interact with us very well. If you drink this, same stuff, right? You drink 4 ounces of it, you go blind. You drink 8 ounces, you die. One intoxicates you, one will kill you. What's the difference? Structure is king. That's why you learned about different naming systems. That's why you care about isomers. And that's when that question comes up, which of the following has different chemical and physical properties? And we're going to see that you can dominate this question now. It's not about memorizing questions, but understanding what's behind them. So, number 5, solid carbon condenses diamond and graphite. Compared to the molecular structure and chemical properties of diamond, graphite has what? It's got to have different structures if they've got different properties. So different molecular structure, different properties. 1, easy, right? Structure is king. Who looked at biology? Those proteins hanging up. When you denatured the proteins and changed their shape, they didn't work anymore. It's the same gosh darn thing. So let's be kind of cool and mosey onto the organic part of the test to see if we can find something like that. So I'm going to go to the same test. Okay, now here we go. 23, carbon-carbon triple bond is found in what? Table what? Who's your friend here? And organic chemistry. Notice I'm a little farther down the test in 23. You learn organic chemistry toward the end of the year. The test goes from 1 to 30. So if I go to what? I go to table P, Q, and A. If I'm from New England, I say A. But we're going to do table Q. Oh, I'm going to miss some of you guys. Okay, so here we go. Alkanes, alkenes, alkynes have a what? So the ines, so it'd be butane. Okay, alkynes. This is weird, me pointing to my finger. Okay, it's kind of weird. Okay? Can I do it? Okay, there you go. So that's an easy one, right? And it changes the structure. Moving forward. Okay, I don't like that. I'm gonna continue on. What'd you say? Oh, thank you. Oh! Well, sure. Empirical is what? Now, both a molecular and empirical. What's a molecular? Molecular is how it exists in nature. For instance, it's had something to do with this. Molecular is exactly how much stuff you have. For instance, if you look at hydrogen peroxide. Hydrogen peroxide is H2O2. You notice that's not the lowest ratio? You would never write that for a salt, right? A salt is an ionic compound with the lowest number of ions, right? We talked about that. Molecular is, the word molecular means molecules, not particles. So in this particle, O bonds O. I call this the eyeglass chemical. That's the actual shape that every single element is sharing electrons. Me and my brother, what? Mongo, fighting for them. There is a what? Bond right here. Sharing equally because they both have the same, not right here would be what? Polar, right. Now, hold on for a second. So this is H2O2. This is how it exists in nature, so that every element, by covalencing, sharing electrons, because they're both nonmetals fighting for electrons, have a stable configuration by sharing. You get that? And it won't always be even. What's its lowest ratio? What's the lowest ratio? Ho! And that's the lowest ratio. Okay, ho! So, But there are elements that are already in their lowest ratio that exist this way. And look at, well, that can be reduced, right? Can that be reduced? Can this be reduced? That can't be reduced, that's your answer. So it's sort of a question. Moving on. I want to find another question like that. Oh! Oh, we've been down this road before. Which formula represents a molecule having a non-polar covalent bond? Are they talking molecule or bond? You better know the difference. So which represents having a non-polar, which means they're sharing electrons equally because they have the same electronegativity. See that? You might read this as which molecule, who is symmetrical, who is non-symmetrical? Maybe you would answer this correct, thinking, well, it's a non-polar molecule. No, the non-polar bonds between atoms of the same element. Careful, okay? You've been down that road. Okay. All right, so let's go back. This is 10, right? Let's go back to 9 for a second, because I'm going to find an organic question that hits exactly what I'm talking about. Maybe. Okay, thank you. Oh, here we go, 25 of 2009. Why am I doing this, moving between tests? Why am I doing this? You can't have a better review because you want to compare tests and see how these things. If you study one test and say, oh, I got that question, but don't understand the concept behind it, you want to see similar questions. Isomers of butane. What are they telling you? They're telling that these are isomers, which means what? They have the same number of stuff but different structure. What do they differ in? Do they differ in their molecular formulas? No. Do they differ in their structural formulas? Yes, that's the winner. Total number of atoms? Okay.